Hi, and welcome to the Splunk Tech Talk on OpenTelemetry. My name is Morgan McLean. I'm a Director of Product Management on Splunk Observability Cloud. I'm responsible for a number of our cross-cutting initiatives, including how we get data in. We rely exclusively on OpenTelemetry for that, and I'm also one of the co-founders of the OpenTelemetry project, which I've been with since its original inception. We're going to talk about a number of things today, beginning with what OpenTelemetry is and the problems that it solves. We're then going to discuss the growth of OpenTelemetry and how it's taking the industry by storm. And finally, I'm going to wrap up with a demo of OpenTelemetry with Splunk Observability Cloud and show you the wonderful functionality and deep insights that you can get from using OpenTelemetry on your infrastructure and your applications. So anyone who's been in this industry for a while knows that while many new developer platforms and infrastructure platforms like Amazon Web Services and other cloud platforms have made it really easy to go and scale out and build out high scale services without having to specialize in the production and maintenance of data centers. This is good. It also has has introduced a lot of complexity for developers and operators alike. Uh, and so when we think of your traditional deployments that you may have, they often branch out across a lot of AWS infrastructure or GCP infrastructure or Azure infrastructure, and you have some on-premises infrastructure, and also various SaaS services that you're subscribed to and using as part of your application. On this infrastructure, you have a multitude, dozens or hundreds or even thousands of services that you've deployed that actually allow your business to operate. This can build quite a mess and can be very difficult to first understand and second to actually manage and continue to build and iterate on and to expand your business. And one of the biggest challenges that customers face here, in addition to just alerting and problem solving, is actually being able to understand what they've gone and deployed. If you ask any engineer or any ops person within a sufficiently large organization, they'll have local knowledge of a few services and the underlying infrastructure for those services that they and their team work on. But those are just one small part of the larger ecosystem. This presents a challenge. If you're running a large business, you probably you feel more comfortable if you have deep insight into all of your services and all of the applications that you're running across all of these different locations. But as I mentioned, this ability to scale that we've unlocked through these various cloud providers has made it very easy to go and build out deployments where no one person in the organization can even hope to gain knowledge of how the entire ecosystem, the entire set of infrastructure and set of services operate together. This is problematic, right? Not only does it make business leaders feel uncomfortable or even the engineers or ops people feel uncomfortable in these organizations, it also means that you're more prone to failures. It means that when failures happen, your outages are going to be longer and significantly more painful. And finally, and perhaps even most importantly, it limits your ability to continue to build on these services, right? When you want to continue growing your business, adding new features, new functionality, if you don't understand how the stack underneath you is built and operates today, it's incredibly challenging and very slow to extend it tomorrow. So we call the ability to view into this observability, right? So it's the ability to look at the different applications and different infrastructure that you've deployed and actually understand how they work and understand their state, understand their performance, and be able to debug them and diagnose them when things go wrong. I like to think of observability like a puzzle. And like any good puzzle, we have many different pieces that we need to fill it in. These pieces are the different types of data that we can extract from our system for analysis. Some of these include distributed traces, which allow you to see how requests propagate across your various different services and infrastructure when a customer performs a certain action. For example, in an e-commerce system, if a customer presses checkout on their cart, this might trigger various different services that are backing the web page or app that the customer is using. A trace will allow you to see this chain of requests. Next, we have system metrics. People are very familiar with these, so like CPU and disk consumption and memory consumption of the underlying infrastructure that's backing your applications. We also have logs. Logs can be generated by that same infrastructure or from your application itself. And we have custom metrics and application metrics that are generated by your application. So think of like latency and request throughput and error rate. And for custom metrics in the e-commerce example I gave, that might be checkout events per minute or even the accumulated revenue from checkouts over a 5 or 10 minute period. These are things that are defined by developers and added to the code. There are other pieces as well. We're not going to talk about them as deeply today, but certainly profiles and network information and others are different signals that we can extract from our applications and our infrastructure to fill in this puzzle of its current state and status and how to debug it that fills in the observability puzzle. Capturing these is surprisingly difficult. If you're not a practitioner in this space, you may think it's relatively straightforward to capture traces and metrics and logs and other data from applications and infrastructure, and that the difficult task is analyzing them. That's not entirely accurate. There are so many integration points, especially when you think of application-specific metrics or distributed traces. There's so many integration points across each language that building and maintaining these tens of thousands of integrations is extremely challenging. This is especially true if we think of distributed traces, where we need to ensure that context is properly propagated across it. I described a trace as a chain of requests. Well, to make this happen, any given service needs to be able to correlate an incoming request with any outgoing requests. And so building these integrations actually presents a lot of difficulty. This is difficult certainly for vendors like ourselves at Splunk, but this is even difficult for end users who at times, depending on the solution they're using, like if an open source stack or even with various vendors, they don't support a certain language, a certain platform, or certain library. In the past, often the burden of implementing this has fallen on these end users. And finally, this is also a challenge for the maintainers of various libraries. Think of the maintainers as something like JDBC in Java, or various storage SDKs or RPC SDKs that you might use in other languages. They, of course, want the users of these frameworks to also get very good observability, and so they're stymied of the same challenge. So building and maintaining all of these integrations is extremely, extremely expensive and extremely difficult, and the industry hasn't been served very well by it in the past. This is where OpenTelemetry comes in. So it's a project that's in the Cloud Native Computing Foundation that looks to extract as many signals and as much telemetry about performance and system status out of backend services and out of infrastructure as possible, so that they can then be analyzed in various solutions. Splunk Observability Cloud is one of those solutions, the one we're very proud of, but OpenTelemetry is certainly a cross-vendor and cross-industry effort. And so it's supported by almost every single vendor in the industry today, which is really, really exciting. And it's a project that's grown incredibly rapidly over the last 2 years. Specifically, OpenTelemetry provides the following. It provides SDKs and APIs that you can use to extract traces and metrics and soon logs from your applications. And so you simply link these to your app and generate the data. There's also instrumentation that you can bring in with these SDKs to automatically capture information from any supported framework. So for example, if you're using like gRPC or JDBC, which I mentioned earlier, or hundreds of others, you can simply link in the SDK, link in the appropriate instrumentation, instantiate it, and you'll start extracting that information really rapidly. We also have a collector. This is an optional component, though incredibly widely used. And the collector you can deploy it as an agent or as a network service, so that it can retrieve data from these SDKs and then forward this information for export to a backend like Splunk Observability Cloud. You can also perform certain processing steps on the data that you've captured in the collector. If the collector is deployed to a host, it will also capture host metrics and host logs from that host. So think of CPU consumption, memory consumption, those core infrastructure metrics that you expect to gather. And there's sort of, I think, alpha level functionality for logging that will allow the collector to also capture system and application logs from flat files on any given host. The collector can also capture information from various other sources. So for example, if you're using Prometheus client libraries to author metrics, the collector can pull those through and turn them into standard OpenTelemetry metrics. Similarly, if you're using capturing distributed traces of Jaeger or Zipkin clients or others, you can transform those into the OpenTelemetry format in the collector. Finally, as an alternative to the SDKs, we also offer some automatic instrumentation components that can extract traces and metrics and logs and other signals from applications that are running on a supported set of languages. Java is one of those. I think .NET is another, and we have a few others that we support. These are certainly a bit easier to use. You don't need to link an SDK, but they're managed usually not directly through source control. And of course, if you want to generate custom data, you'll still need the SDK anyways. OpenTelemetry has a specification that defines the data structure and operations that you can perform on the data that it captures. It also has a line or a wire protocol that serializes this information and can send it between different OpenTelemetry components. This is how the SDK and the automatic instrumentation components can send information to the collector. Finally, we have exporters in OpenTelemetry. These exporters allow you to send this data once it's been captured inside of the collector, or even directly from the SDKs if you choose, and send this information to a backend for processing. For example, there is an exporter for Splunk Observability Cloud that sends traces and metrics and soon logs that are captured from various OpenTelemetry components, typically the collector, to Splunk Observability Cloud for processing. There's a lot that comes out of the box in Splunk Observability Cloud. And so when we think of the list of reasons why end users should care about this beyond just vendors, that out-of-the-box functionality is certainly one of the biggest reasons, right? You can capture traces and metrics and other application infrastructure information from effectively any source that you're running and put that into a normalized format and then send that to any backend. And it works great out of the box. To that end, OpenTelemetry with the collector and the SDKs includes effectively everything that you need. This is not just a set of interfaces that you use where you combine different components. OpenTelemetry has everything that you need right out of the box. It's very easy to get started with. The fact that it also captures distributed traces and metrics is important, particularly when you think about existing Splunk customers who are used to Splunk Enterprise or Splunk Enterprise Cloud. Capturing logs, typically systems logs in Splunk Enterprise via the Universal Forwarder, is certainly important. But the Universal Forwarder hasn't historically supported distributed traces or metrics or other data types. These can be more challenging to capture than logs due to the number of integrations that I outlined earlier. And so OpenTelemetry provides a really robust solution for this that certainly Splunk and other vendors didn't have previously. Another key part of OpenTelemetry is the fact that the data that it captures and that indeed the metadata that's stamped onto that data is very consistent. This means that you can perform correlations between that data. For example, if you capture a distributed trace that hops across various services, you also know the underlying infrastructure from each of those services because that metadata is stamped onto each span of the trace. That allows you then to correlate that with logs or with infrastructure metrics that have been captured from that same infrastructure. Surprisingly, this has not been common historically, particularly with open source solutions in this space. And so being able to correlate information across your application stack down to your infrastructure stack and do so in a consistent manner is incredibly powerful and is a gap that has existed for a long, long time and has been stymieing various analysis solutions prior to OpenTelemetry. So this is a major impact of OpenTelemetry that simply cannot be ignored. And finally, I think we land on the fact that OpenTelemetry offers extreme flexibility. Because you can export the data in OpenTelemetry to any supported destination, which is effectively at this point any destination you could ever imagine exporting it to, OpenTelemetry allows you to do a number of things that you couldn't do in prior solutions. For example, if you use OpenTelemetry with various vendors or a set of vendors for analysis, as well as open source backends for processing, like say Prometheus and Jaeger and Zipkin and others, you can easily transition between them with OpenTelemetry without changing your code. By simply pushing a new configuration file to the collector and ensuring that the collector has the appropriate exporters there, you can send this data to different destinations, which means if you want to change vendors or change these destinations, this goes from being incredibly difficult, where you'd have to rebuild and redeploy all of your apps and redeploy your infrastructure, to incredibly simple and just being a simple configuration change. Next, you can also use more than one backend at the same time. There's no limitations on exporters in OpenTelemetry, and if you choose to use different tools across different teams, one of the incredibly powerful new things that OpenTelemetry can bring you is the ability to have teams choose their own tools, but still maintain visibility across everything you've deployed. Historically, if you wanted to allow teams to choose between different vendor solutions or different open source APM solutions and others, you would have had to, they could only see a local view. They could only see the services and infrastructure that they had deployed because you wouldn't typically want to run multiple agents at the same time. OpenTelemetry allows everyone to get extreme visibility into the system across all of its breadth, no matter what processing solution or backend solution or APM or monitoring or logging solution that they're using to analyze this information. So I've told you a lot about OpenTelemetry. We're now going to dive into a demo about how we use it with Splunk Observability Cloud. Again, OpenTelemetry is a pure open source solution. It's got a number of huge companies, including Splunk, leading the way in its development. And so you can use effectively any backend of your choice to process this data. But Splunk Observability Cloud was built with OpenTelemetry in mind. And so I'm going to show you with these correlations and the power, the flexibility that you get with OpenTelemetry, the types of deep analysis that we can show to you. So I've jumped into Splunk Observability Cloud's APM view. To clarify, this is simply one of the different lenses or experiences that we offer within Splunk Observability Cloud, but it's likely the one where we can most quickly demonstrate the value of OpenTelemetry. What I've deployed here is a variant of Google's Hipster Shop e-commerce demonstration. This is a Kubernetes application that's running, I think in this example, is technically running on AWS and Kubernetes, and it's a mock e-commerce system. So it has various services written in different languages that operate effectively as an e-commerce system and allow us to toy around with it and analyze it. In this APM view, we can see a lot right away. We've already instrumented this with OpenTelemetry, which is giving us our data. And with that, without any additional hints or any additional work, we've detected the various different services that are present inside of this e-commerce application that's being deployed. And we've also detected various different business workflows. Business workflows can be defined custom. In this case, we're just pulling up the automatic business workflows, which correlate with the different HTTP paths or HTTP routes that are endpoints that are exposed within all of the services, as well as any gRPC methods that are exposed on these services. So you can see the actual operations that occur on each service. We've broken out each of these by error rate and latency across the services again and these business workflows. And if we scroll down on this page, we can actually look at an individual service and get a deeper view of its latency and its request and error rate. So right away, OpenTelemetry has given us a deeper view into our application, and it's been very easy to set up. But I want to go even further. And so when I click Explore, I can see the application topology map. What this shows are the various different services that I've deployed within this mock e-commerce application and their interactions. Again, 100% of the information gathered here was pulled in from OpenTelemetry. We've done no special modification. We've provided no special hints to the system. This was done automatically and just for us. And just by setting up our instrumentation, we were able to generate this view. And from here, we can learn a lot about the application, right? We can see how the front-end service interacts with the checkout service and how that interacts with the payment service and so on. If I mouse over one of these services, I can get a hint and overviews into their interactions. And the same occurs as well if I mouse over one of these connections here. In this example, we can see that we have some slowness here between the front-end service and the checkout service and the payment service. And certainly we can use Splunk Observability Cloud to dive into that and to analyze why. I'm not going to do the full analysis here because we're focused on OpenTelemetry, but I will do a more rapid analysis. And so by diving into the workloads, we can filter this down to just look for checkout events. From here, we've pruned the graph to only show nodes that interact with these checkout events. This is really, really important. So because these checkout events are captured by OpenTelemetry as a tag on various traces, we can actually determine from a given interaction with the front end or even a given interaction with the client, which here is instrumented with OpenTelemetry as well and is giving us information, we can determine the impact on our leaf or bottom level services within our broader application. This is not something that we could do with simple application metrics. And indeed, if we weren't propagating tracing information with OpenTelemetry and not propagating down tags and baggage and other information, we would not be able to generate this view. And just to clarify even further to show the power of this, when we look at, say, the latency between front end and checkout, this is only for these checkout events. Similarly, if we look at the latency between the front end service and the checkout service and say the shipping service, again, this is only for these checkout events. I realize in this simple application that might be the only events that would occur on these routes. But if there were other request paths here, they have been pruned out, and the latency numbers that we see here have been updated to reflect that. And so right away from this graph, we can learn a number of things. We can see that the checkout service is slow, 4.15 seconds of average latency. And by average here, I think we're referring to P90, 90th percentile latency, which is totally unacceptable for an e-commerce application. From here, we could dive into distributed traces to form a deeper hypothesis about why this was happening. But in fact, with the graph, there's no need to go to that level. With the power of OpenTelemetry and these insights it's generated within the Splunk Observability Cloud, we can quickly see that the checkout service is slow for two reasons. First off, we're generating a high error rate and high latency between the checkout service and the payment service. We'll need to investigate that. We have even higher latency between the checkout service and the cart service. Similarly, the cart service to the Postgres, this Postgres database that we have called Galactus, is extremely slow. And so, just with the, with just instrumenting our application with OpenTelemetry and doing a basic analysis within Splunk Observability Cloud, we've avoided diving into distributed traces, though we certainly could if we chose to. And we've looked at this really intuitive interface that allowed us to prune down the cases of high latency and find out why they're happening. I can also dive in even further. So we can see here that the error rate on the payment service is relatively high. I talked about correlations earlier when discussing some of the benefits of OpenTelemetry, and I can show that right here. By clicking on the payment service on the bottom bar, we've now shown content that's related to that. And so with one click, we could jump to the infrastructure view for the payment service or to logs captured by the payment service. I'm going to open this in a new tab, but we'll come back here that we'll come back to in a few moments. But first, I'm going to show you some even sort of deeper correlations that we can form. So I've got the payment service selected. That's also changed the bar on the right here. By clicking View Dashboard, I can view an automatically generated service dashboard for the payment service. This shows at the top the kind of information you would expect in an APM product, like request rates and latency and error rates over time. But if I scroll down, I can actually start to see host information. Again, I talked about correlations from OpenTelemetry. This comes in from OpenTelemetry, and because OpenTelemetry correlates application metrics and application distributed traces with infrastructure, we can actually see the core host metrics for the host that's backing this service. Here, nothing looks out of whack, and that fits with what we would have expected from the application map. If I scroll down, we can also see related Kubernetes metrics because, of course, the service is running Kubernetes. Again, nothing here untoward. That's not what we would have expected. So I mentioned before I had opened logs in a new tab, and so we can use this to dive into some of the errors that are occurring on the payment service. Again, by taking that related content link that was provided to us by OpenTelemetry because of its underlying metadata, I'm just looking at the logs for the payment service here. And so if I look at these, we see a high number of errors, and if I choose to, we can certainly sort through some of the metadata here. But I want to just look at the errors for the service because I know the latency is high. And so by filtering this down, we can rapidly see that the payment service has failed payment processing through our Buttercup payments service that's even further downstream due to an invalid API token. If we go into the traces, we can see that this is due to a retry loop that occurs until these requests succeed, which is causing the high latency. But from this, we've determined that our fix needs to go and update our API token. So just to wrap up, using OpenTelemetry, I was able to quickly diagnose the issue that was occurring in my broader application and isolate that to high latency between my payment service and one of its downstream connections that then was related to a Postgres database, and a high error rate in another service. I was able to do this intuitively without having to manually dig through traces or various metrics because of the information that's captured by OpenTelemetry. And finally, if I wanted to use another tool in conjunction with this, or archive the data somewhere else, or have different teams use different tools, OpenTelemetry will allow me to do that. So in this demonstration, I hope you've gained an appreciation for how easy it is to get started with OpenTelemetry and the power that it gains you, and why we decided to build our entire Splunk Observability Cloud experience around the power of OpenTelemetry. I hope this was an insightful experience for everyone and that you gained a great appreciation for OpenTelemetry, its power, and certainly why it's growing so rapidly in the industry. The project is only 2 years old, and it's already now the second most active project within the Cloud Native Computing Foundation, just after Kubernetes. That's something we're really, really proud of, and we think it really shows off the interest that people have in OpenTelemetry and the impact that OpenTelemetry has on them. So thank you very much. Have a great day.